warm and pleasant evening to today's resource person, Mr. Kumar Pandey, respected Professor Kuldeep, Professor NIT Hamirpur, respected Madam Pragya ji, Madam Minakshi ji, all esteemed members of organizing team, dear participants. So I'm here to welcome you to the third day of our workshop on behalf of the organizing team. As we continue this enriching journey together, I hope you are strengthened and inspired by the engaging discussions and insightful sessions we have experienced so far. Today, we are privileged to have with us our distinguished resource person, Mr. Jeevan Kumar Pandey. Mr. Pandey is an accomplished physics educator with over 22 years of rich teaching experience. He holds his master degree in physics from National Institute of Technology, Rourkela, and is an active member of resource team of National Anveshika Network of India under the mentorship of Professor H.C. Verma. His passion lies in experiential learning, where he beautifully transforms everyday materials into effective teaching aids, making physics not only understandable but truly enjoyable. Through numerous workshops, both online as well as offline, he has consistently promoted innovative pedagogy, hands-on exploration, and activity-based learning. So today's theme is rotation. That does the axis change that story? Invites us to rethink some very fundamental ideas in motion. Together, we will explore exciting questions that are, is angular momentum an inherent property, or does it depend on our perspective? Why does the same motion appear different from different reference points? Can rotation speed up without any apparent cause? And is circular motion really as simple as it seems? So very exciting question. And this session promises to challenge our intuition and deeper our understanding. I am very confident that today's session will be as engaging, as thought-provoking and enriching as the previous ones. With great enthusiasm, I invite Mr. Jeevan Kumar Pandey to take over the session and guide us through this fascinating exploration of rotation. So, sir, I invite you to start. Over to you, Jeevan, sir.
Ji, ma'am. Thank you, ma'am. First of all, I take this opportunity to thank IIPT members for giving me this opportunity to be a part of this wonderful learning experience. Respected Meenakshi ma'am, respected Nitu ma'am, and Pragya ma'am. The first 2 days I really enjoyed a lot. The finer details of simple situations that were brought in by ma'am were really enriching, and that helped us rethink the way we need to put the discussion in front of our thoughts. Today's in the introduction, all of us we have seen that today's topic will be circling around the topic of rotation, rotational dynamics. Chiefly, I'll be considering the concept of torque, angular momentum, and so on. See, this topic in plus two students, it is a very detailed topic. Now, some topics are though deleted, like rolling, etc. We'll be taking up this thing. But before I start the topics for the agenda for today's discussion, I would like to present an activity first, just as a recapitulation of the things. Yesterday, the last 2 days were based on Newton's laws, work, energy. Such situations were dealt in. Now, from that, we are shifting ahead to rotational dynamics. Just to keep ourselves ready, to make ourselves ready, let us see first an activity and then we'll have a discussion. This will help us revisit the concepts which we have discussed in, which we have uh, seen in rotational dynamics. This is a, I would request to pin my video so that this screen is visible to all of you. Can you see there is a wooden block? Is it visible?
Yes, yes, sir, it's visible.
So this I will be using as an inclined plane, and you can see this is a support. I can say wooden support. So one end of this wooden block, I'll put this wooden support. So this end is higher, this end is lower. So this constitutes our inclined plane. Now I have something over here, a cylindrical jar. Can you guess what is present inside this jar? There is something which we eat.
Sugar,
Rice.
rice, rice.
Yes, it is rice. And I have another similar jar that also has rice. In rice, there is nothing special about rice. You can take dal, spices, anything which is available in your kitchen, you can take that. And I have one more such jar. This one, this is completely empty. Uh, it is not having any rice. So I have three jars. One is empty. Of course, it has air. One is having small amount of rice in it, and one is filled with rice. I have completely packed it with rice. It is completely packed, completely empty, and in between, like so. Now the hollow one, if I roll it, if I put it over here, as expected, it is supposed to roll, and this is what we observe. Now, instead of this, if I take this jar filled with rice, do we expect this to roll? What is your take? One more thing, I would be happy to receive uh, discussions. Interactive discussions will help me guide the webinar in a proper way.
It
So,
also
can we
rolls
expect
down.
this free? It
Yes, sir.
should
It
roll.
will
Let
also.
us see. Both of them roll. Now, can you have any idea? Let me show you also. Which of the two takes lesser time?
The heavier one.
Empty, empty.
Here one takes lesser time. Okay.
Empty jar.
Sir, I
Empty
think
jar.
both will take the same time because the acceleration of both the jars should be same.
Now this I leave to you to do it physically. Up calculation, you can do the calculations. You can, of course, they have different masses. Radii are same, masses are different. Whether they will take same time or not, this might be one of the assignments for you. But experimentally, let us see. I'll release them together. Yes, there is some time lag. It seems there is some time lag, but not much. They almost take the same time with the heavier one leading slightly. So it takes less time. It takes slightly more time, almost equal time, but slightly different. Next comes the third jar. Now let me call this time as T1, which is less. Time taken by this jar be T2, which is more. And let the time taken by this third jar be T3, let us assume. Now you have to guess before I roll this, the time taken by this jar will be l- between these two, less than the least, or more than the maximum. What is your guess?
Sir, although time acceleration doesn't depend on the mass, but I guess the half-filled jar will have something which will change its moment of inertia over its motion. So there will be something which we cannot guess physically.
At least we can guess. At least we can guess, I believe. It may
Okay.
be correct, it may not be correct, but we can guess.
I
Let it
think,
be a
sir,
wild guess also.
The properties of the third jar are somewhere in between two.
So less, I guess less,
In
Let
between,
us
more
assume
time.
this time to be. Let us assume that this time is 9 seconds. This time is 10 seconds. Let us assume that
Hmm.
9 seconds and 10 seconds. So we have three options
in
between
between
9 and 10.
9 and 10.
Okay, more than 10, less
So
than 9.
more than 10.
No,
Between 9 and
between 9
10.
and 10.
Between 9 and 10, probably.
And the logic which I can presume of this answer is that it has mass somewhere between the lighter one and the heavier one. So its time should be between this and this. Knowingly or unknowingly, we are trying to have this logic in our mind.
Yes.
Anybody more than 10? More than 10 seconds?
Yes, more than 10 seconds.
Okay, and why do you say that, ma'am?
Because the container is like one-fourth full, we are expecting its center of gravity to shift as it is rolling, as a result of which it will result in a wobble, if I might say. So that results in uneven
Okay,
motion, hence time taken would be more.
okay. Very nice logic. Uh,
Thanks.
I appreciate the logic. Okay, but I am not sure it is correct or not. But I appreciate the logic. Uh, any answer which is less than 9 seconds
I think it would be less than 9 seconds.
would be less than 9 seconds. And what could be the logic of behind that, ma'am?
So, as similar to Arundhati ma'am, but I think that the rice particles inside it has the space to move, so they may
Okay.
push more towards the uh, direction of motion. So it will have more acceleration, adding the acceleration of those particles also inside them.
If they're pushing against the walls of the vessel,
Yes,
then I should expect more push in this
but
filled
they
jar.
are not moving; they are fixed.
Okay. Relative to the jar, they are not moving. You wish to say
Yeah.
that. So let us bring an end to this discussion by observing what happens. So this is my jar. At the count of three, I'll release it. Let me release it with the uh, jar. 1, 2, and 3. So something happened here. It didn't roll. Let me try it once again. It resists to roll. It says, no, I don't want to roll. The filled one, very happily it rolls. The empty one, equally happy to roll. But this third jar, uh, it is behaving in some very peculiar way, a non-intuitive way. Even if I try to push it, you can see I try to give it a jerk, but it completely denies my instruction. And wherever I keep it, it tends to stay there. Now, this activity, if before starting rotational dynamics in class, if you put this activity in front of the students, I don't say they will learn something, but at least it will certainly draw curiosity in their minds. They'll be interested, and it doesn't take much time. What you need are three jars and rice. Now let us consider why this happens. One answer I received, wobbling effect, that can happen. That can happen if I change the inclination, something like this. You can see. So the angle of inclination is also important. Here it is not rolling. I am increasing the angle. Now it is rolling very slowly. I increase the angle further, and it is slow. I'll consider the case where it was at rest. Now to discuss that, let me first share my screen. Well, one thing that is common in the first and the empty jar and the filled jar. What is common in these two jars? Can somebody help me?
Position of center of mass.
Yes, position of center of mass. Their masses are different, but they are identical in one respect, that their center of mass is almost at the geometrical center, which I write as G. So this is the case of filled jar or the case of empty jar. For both of them, the discussion remains the same. Now on this incline, let us assume the angle of inclination be theta. What are the forces acting on this jar, whether empty or filled?
So friction force.
mg
Please
normal
lift
friction.
your papers.
Okay, friction I received, gravity I received. Will there be normal reaction also?
Yes, sir.
Yes, sir.
Yes. Now, if friction will be there, in which direction should I point the friction?
Along the incline up.
Up the incline. Okay.
Upwards.
Upwards.
So this is the direction of friction at the point of contact. Point of contact, I can mark it as say P. Gravity, of course, it will be vertically downward. And at the point of contact, there will be normal reaction. That normal reaction will be like so, N. Now, let us see whether or not there is net torque about point P. Now, why it is important to say about point P? Torque is observer dependent. From which point we are finding the torque, that is very important. So from our basic definition, we know that torque is the cross product of R and F. Now this R is the position vector. So from which point that we have to analyze. So we can choose any point, of course. I am choosing for point P. Can you tell me, if we measure the torque about point P, out of these three forces, which of them will provide the torque?
Gravity.
The weight.
As measured from point P.
mg.
Friction?
Mg. And why not friction and normal reaction?
Passing through point of reference. Cross product 0.
Yes. So we are finding the torque from point P. So the frictional force itself is passing through the point of contact. So the torque due to frictional force must be 0. Likewise, can I say that the torque about point P due to the normal reaction is also 0? Do you agree with this?
Yes, sir.
Are you convinced that the normal reaction will produce 0 torque?
Yes, sir.
Yes, sir.
And then gravity. Gravity is not passing through point P. So there will be some perpendicular distance. Let me call that perpendicular distance. Let me mark this distance as D. Then the torque about point P due to gravitational force, that will be how much? The force times the perpendicular distance, that is mg, times D. And this torque will tend to rotate the jar in this sense. So its omega will be in this sense. Now if we add all these three, see the net torque about point P will be sum of these three torques, that will be torque due to mg, and that will be mgt, which is not equal to 0. Since this torque is not equal to 0, there is net torque, and that torque will result in change in angular momentum as measured from point P, and that's why this jar rolls. It rolls down the incline.
So
Now coming to the yes.
So why we are interested about point P, not from G? Because from G it would be easier, like two forces, torque due to two forces, normal and mg will cancel out.
Yes, sir.
And only from frictional force it will remain.
Sir, there is nothing special about point P. This could have been discussed from point G, and not only point G, we can take an arbitrary point. You are right. I could have chosen an arbitrary point O. So you could have discussed from point G, no problem at all. No problem at all. But the effect remains the same. If you take it from point G, then N and gravity will produce zero torque, and there will be torque due to frictional force. And that will give the similar result, similar calculations, same time, everything. Any point can be taken, sir. Now the interesting part. As during the illustration of the activity, you cited that the center of mass will change. The blue dot represents the original center of mass of the filled jar or the empty jar. But when we had that jar which has a small quantity of rice, 1/3 was rice, the rice layer will be tilted like so. This is rice. And because of the accumulation of rice particles at the lower end over here, the center of mass of this entire system shifts to a new position, which I write again as G. This G has been represented by the dot, red dot. Let us revisit the things again. As discussed in the earlier case, here also we'll have the same set of forces. So gravity, now instead of earlier point, now it will be acting vertically downward, mg. Friction will be like so, up the incline, and the normal reaction from the point of contact will be like so, passing through the center. This. Now, what is the important difference between the case 1 and case 2? If we try to find torque about point P.
Point of application of forces.
Yes. In first case, you can see the main difference was this, that while normal reaction and friction, both of them were passing through this point P. But gravity was not passing through the. But in second case, even the gravitational force mg, it is so adjusting itself that it passes through the point of contact P, and that creates this effect. So the torque about point P due to friction, torque about point P due to normal reaction, and torque about point P due to gravity. All of them, each of them has to be zero. Why? Because each of these three forces, the friction, the normal reaction, the gravity, all of them, they pass through the point P. Now, in this case, in second case, as sir you were saying, now it becomes easier to discuss the rotational equilibrium by considering point P here, because all those forces are passing through point P. But there is nothing special about point B. You can choose point G as well. You can choose point O as well. Some of them will give positive torques. Some of them will give negative torques if seen from O. And the net torque has to be zero, irrespective of the point we choose. Since there is no net torque, we cannot expect any rate of change of angular momentum. And since there is no change of angular momentum, initially it was at rest, so it is expected to remain at rest. And this is my submission regarding the explanation to the fact why the jar which is filled with 1/3 portion to the rice doesn't will to roll. It doesn't wish to roll. So should we proceed further?
Sir,
Okay, sir. Yes, sir.
sir, is it necessary that mg would pass through point P?
No, it is not necessary. But if mg does not pass through P, sir, you can try this activity at your home. What will happen? that there will be net torque, and it will rotate slightly. As it turns, there will come a situation immediately such that the gravitational force that will pass through point P, point of contact.
Sir, but
In fact,
this
it might.
uh, Sir, but this would
Yes,
also
sir.
happen that it is not necessary that normal reaction should always pass through point O. It sometimes happens like we discuss the equilibrium of a block placed on an inclined plane, and we do not pass the normal reaction through the geometric center because we have to balance the torques. And in a similar situation, the normal reaction here also should can displace from the center to make the net torque on the cylinder zero.
A very good logical comparison between. I hope, sir, probably you are saying about this, that there is some block and it's not necessary that normal reaction passes through its center of mass under some situations. That is shifting of normal reaction. Agreed. But whether the normal reaction is here or here or here, it has to be normal to this surface, which on which the block is resting. Likewise, this normal reaction in our figure must be normal to which surface? To the surface of the incline. Now this we are assuming that this sphere has a single point of contact. It doesn't have a area of contact. If it has a point of contact, then we know if a sphere or a cylinder rests on an inclined plane, then this inclined plane is the tangent. And if it is tangent, normal to that tangent, normal to that tangent must pass through the center, because we know radius and tangent are perpendicular. So in this case, of a cylindrical jar, the normal to the inclined surface must pass through geometrical center only. It cannot be like this. It cannot be like this. But a very good point raised by you, sir. But in this case, the normal reaction has to pass through the center, because normal reaction has to be perpendicular to the of the inclined plane. So this was the comparison. Rest, sir, we all can try this activity at home, and it's interesting. As I was showing, I did not show at that time. It might happen sometimes that this jar rolls up for a very small distance. It will depend upon the position of the center of gravity. Suppose this is your jar, and your rise happens to be something like this. Then the center of gravity will shift to such a point over here. This will be your center of gravity. And the inclined plane is like this. Normal reaction will be like this. Frictional force will be like this. But the torque due to the gravitational force will not be zero in this case. In this case, what will happen? The torque by mg about point P, you can see, it will try to rotate in which sense? Can you guess from this figure? Will
It
it
will
turn
climb up.
in this sense or this sense? Yes, it will be in clockwise sense. So the first point which you had raised, in this case, what will happen? It will turn in this sense, not in this sense. And how long will it continue? It continues this journey. When it continues this journey, the center of gravity will start shifting this side. And when it shifts this side, one point will come when this mg will exactly pass through the point P. But it will be a cherishing moment if you try to do this activity on your own, and you will find that first it rolls up slightly and then comes to rest. It may roll down also initially. That depends if the situation is something like this. Your rise happens to be here. Then the center of mass will be somewhere here. Now the gravitational force will be here. Point of contact is here. So this time the torque will be here. But even in this case, it will turn, and after some time it will attain this configuration.
It
Once
may
that
be
configuration is attained,
oscillating situation also, sir, right?
huh, but with that oscillation will die out very quickly,
Yes,
and it
yes.
will come to rest in this. It will come to rest at that orientation in which gravity will exactly pass through the point of contact.
That would be stable equilibrium then.
That will be stable equilibrium. Rightly said, sir. I
So
hope we
it
are.
would not surpass that equilibrium configuration.
Sir, as I showed in the activity, it will depend on your angle of inclination. It might be possible that if you increase this angle of inclination to a large value, if this angle happens to be say 80 degree, 85 degree, then you might not expect rolling. It will simply slide. So all those things can be brought about, and a lot of things can be discussed with the students. Now, from this particular activity, what we can discuss, we can establish the conditions for rotational equilibrium. We can discuss about the relation between torque and angular momentum. Then we can discuss with the students how the torque is becoming zero in this case and not zero in other case. Then we can discuss the effect of change of angle of inclination, all those things. This was just a warm up for today's activities, and the real cherishing moment will come when we try these on our own, when we let our students complete them on their own. Now, the main agenda for after this warm up, the main agenda for today's discussion is validity of the relation L is equal to I omega. Now, this is a very common uh, formula which seems to be, now I'll say which seems to be rotational analog for the equation P is equal to m into v. Momentum we replace with angular momentum, mass we replace with moment of inertia, linear velocity we replace with angular velocity. But my main discussion for today's webinar will be based on this single relation L naught is equal to I omega. To begin with, you can see a figure over here. In this figure, you can see there is a bob. Let us assume it to be a particle, point-sized particle, having mass m, and it is moving in a circular orbit. C is the center of this orbit, and the axis of its rotation is represented by this line, that is OC. And it is given that the mass is moving with speed v, which is constant. This speed v is constant. I is its moment of inertia, and omega is its constant angular velocity. Now there are 3 points. It's like a pole. I'll take a pause here, go through this statement, and in the chat box try to put your answers. And I'd request Neetu ma'am or Pragya ma'am, if you could help me, because I'm not able to see the chat to receive the
Okay, sir.
answers.
Okay.
So the question is, select a point about which the angular momentum, about which you think the angular momentum of the revolving particle is constant or conserved. 3 options are given. Option first is O, B is C, and third option is any point on the orbit. You have to choose such a point about which angular momentum is conserved. More than one options may be correct. And there is nothing to haste. Please take your time. I'll pause for a couple of minutes, then give your responses in the chat box.
Sir, one question is gravity considered?
Is gravity considered?
Do we need to
See, the
consider
situation
gravity?
is very much
Query
clear
from
here.
someone.
It is a horizontal circle. It is a horizontal circle. So it is revolving. You can take off a situation of a string tied to a mass, but it is horizontal. Planets revolving around sun, something like that. Satellites revolving around this, electrons revolving around nucleus.
The answers in as
The
per the
mass,
chat box, the answers are B, C, A, then again A.
okay.
A option means, or answer is O. Then some are saying C. So please mention whether it's a C option or a C point. Dear participants, please mention it.
We will wait for some more time. And those who have already responded, you can change your responses also. Because this part is more important. Let the situation sink in your mind, and don't bother about what others are mentioning. Okay, I think we should start discussing now. So, ma'am, most of the answers are, I think, which one? A. Nitu, ma'am, can you help me in identifying most responses? Am I audible?
Yes, sir.
Yes, sir.
Am I audible, ma'am?
Yes, sir, you are audible, and it's a mixed response. A, B,
Okay.
C, almost all are equal. Means A, B, yes.
That means that means it needs to be discussed properly. So
Yes.
I request sincere attention from everyone. Let's go by one by one. So this is our situation. Let's first consider point. We have to find angular momentum. Now, what is the basic formula for angular momentum? That is our L vector about point O is equal to R vector as seen from O cross the linear momentum of the mass, that is P vector. And how do we write P vector? P vector is nothing but mass times its velocity. Now, considering this orbit as horizontal, let me mark an arrow to help you identify the direction of sense of rotation, like so. First, you tell me the direction of P vector. That is same as the direction of velocity vector. Velocity vector has to be along the tangent. At this point where this mass is located, at this point, what is the direction of velocity?
Into the screen.
Into the screen. So can I represent it like a cross? Cross means it is into the screen, perpendicular to the plane of the screen, away from the reader. And our position vector from O on to M is this one. This is our R vector. Now, using our basic knowledge of cross product R cross P, R vector is in this plane and P vector is by cross. It is tangential. So, what should be the direction of R cross P? We know it has to be perpendicular to both R vector and P vector. So, can you guess? You can use your right hand rule and help me in determining the direction of L vector.
So in the same plane but perpendicular to R.
Okay. Now, perpendicular to R can be this way
Opposite
or that
way.
way.
So second.
Oh, yes, sir. So this is L vector as measured from point O. So we say that L vector will remain constant during the entire journey of the mass as a vector.
So it will change.
Suppose this mass after some time comes to a diametrically opposite point over here. Then similar argument will say that the angular momentum vector as seen from O will be like so. it is clear that the direction of angular momentum is changing. Let us not discuss about its magnitude right now. Its direction is changing. If its direction is changing immediately, what we can infer? We can infer that it is not constant vector. Its magnitude may or may not remain constant. We will discuss it afterwards, but its direction is not changing. The first option about point O, the direction is changing, and hence we will say no. As seen from point O, it does not remain conserved. Let us now switch over to second point. Second point is C, the center of a circular orbit. Now we'll continue our discussion, and the process remains the same. As measured from point, this will be our R vector. And the P vector or velocity vector will be directed into the screen like so. R vector and V vector, if you find cross product, what should be the direction of angular momentum?
Perpendicular to plane of circle. Up.
Perpendicular, normal to the plane of circle, and
Yes.
it will be perpendicular to both R vector and P vector. So I hope all of you agree to this, that the angular momentum as seen from point C will be like so, LC vector. When the mass comes over here, again we can see this will be our R vector, and this time the velocity vector will be coming out of the screen. So R cross C vector or R cross P vector will again be outward as measured from point C. Likewise, if the mass is over here, everywhere we'll see, you can yourself observe that the angular momentum as observed from point C is not changing its direction. Direction is same. Now, since the situation is symmetric as far as point C is concerned, the point C is at equal distance at all times from the mass. So R vector will change its direction, but R vector magnitude will remain same. So when we calculate the magnitude of angular momentum as measured from C, magnitude will be mv, that is magnitude of P into radius of the circle into angle between them, which is sine 90. So this becomes mvr. At any point the remains mvr, r is remaining same, v is constant, mass is not changing. So it has a constant magnitude, it has a constant direction. So what should be our take this? Okay. When we see the object from point C, angular momentum is conserved. So LC is constant. So should we proceed further? And third one, can you respond why it should be constant or it should not be constant? As measured from any point. Oh, something happened. Wait. Is my screen visible?
Sir, you are visible
Yes.
now. Screen is not visible.
Screen is visible, sir.
So screen is visible.
Okay.
Thank you.
Now let me hear from you, based on these two discussions, what can we infer about the third option?
I don't think it will be conserved, sir, because the perpendicular distance itself will change depending on where the mass is on the orbit.
Yes. Yes. See, if I choose a point, say P, let me consider a point P. It's very easy to see that this is R vector and P vector is into the board or something. So there will be some value of R cross P. We will get some non-zero value of angular momentum. But this mass, when it turns, after some time, it will come to point P. It will make a journey, it will travel through this through its orbit, and at some time it will be at this point. When the mass itself is at this point P, then its angular momentum as measured from the point P itself has to be 0. And for any other position of the mass, its angular momentum is not to be 0. There will be, and moreover, its value will keep on changing as you suggested. So any point on the orbit, no, its angular momentum will not be constant. So what we observed that in this case of a single particle revolving around a circular orbit, its angular momentum will be conserved only. L is conserved only about a particular point, not all points, and that point is C. This is our first takeaway from this discussion. Second takeaway is that angular momentum of a particle, it is observer dependent. It depends on the observer. Where is the observer? Whether he is at point C, point O, or some other point, it depends on that. The same discussion. Yes,
Sir, sir, but about point O torque net torque is also 0.
no, sir. Acha, why do you say torque is 0?
Sir, if it is tied to a thread, then centripetal forces towards point
Center.
O, and
No, no. Sir, okay, sir. First to continue. Sir, towards O or towards C?
towards C, I guess.
Yes, yes.
Okay,
Sir,
okay.
I think what I want to say, better you say that. Please continue this. Centripetal force will be towards C,
Yes, sir.
and this is R vector. This will be our R vector as seen from point O. So torque as seen from point O, can it be 0?
No, sir.
No. Since torque is not 0, now this is a very good logic, excellent logic. As measured from point O, torque is not 0. Why torque is not 0? Because the force is directed towards C. Since torque is not 0, I can write dl by dt is not 0. And since dl by dt is not 0, that means dl by dt is something. That means L vector is changing with respect to time. And the same argument, exactly same argument can be uh, told for point number C. Let us check it out for point B. What is point B? Point B says C, about point C, center of the circular orbit. When seen from C, so if this be the orbit, this is C, wherever the mass be, here or anywhere else, we know if a mass is moving in a circular path. I don't know about this situation, whether it is planets revolving around the sun, electrons revolving around the nucleus. If there is a circular orbit, what should be the direction of net force? It has to be towards the center. This is the direction of force. And if this is the direction of force, if it is towards center, as measured from C, R vector and F vector are anti-parallel. They are anti-parallel. Always, any location of mass you can see. And in this case, if they are anti-parallel, angle between them is always 180 degrees, and therefore torque as measured from point C will have a magnitude equal to R times F times sine 180 degree, which happens to be 0. Now, since torque is 0 about point C, therefore the angular momentum must remain conserved as measured from point C.
Sir, mg will also create torque.
Sir, just a minute. I'll come to that point. D by dt of LC has to be 0 as measured from point C, and that's why LC has to be a constant. Sir, what I argued, if we see there will be a gravitational force, yes. But if there is gravitational force in downward direction, I hope you are considering the motion of a mass attached to a string. So there will be tension in the string, there will be gravity, and in that case, the mass will move in a circular path. But even in that case, when it is moving in a circular path, the net force has to be towards the center. Net force. Here the F which I have represented, it is the net of all the forces. If the net force is not towards the center, it cannot move in a circular orbit. So the situation which I had given in the first case, here we are discussing such a situation wherein the mass is moving in a circular orbit. I have not mentioned about forces. It is understood that if it is moving in a circular orbit, howsoever number of forces might be acting on that object, if it is moving in a circle, the net force has to be towards the center, the resultant force. And that force will produce zero torque about point C, only point C. And that's why its angular momentum will be conserved only about point C. So based on this, we can say that when planets revolve around the sun, of course, we assume sun to be at the focus. So it is only the location of the sun from where the angular momentum of the planet Earth can be treated to be conserved. If I choose some other point on the orbit, say P, say O, say T, from these 3 points, if we measure the angular momentum, it will be different at different instants of time. Only from point S, we will observe that the revolving planet will have a constant angular momentum. So let us now go ahead to the next situation. Slowly the things will become more involved. And now I'll request other participants also to interact. And if you wish, we can take a pause also for this question. Same situation of a mass revolving around the center C. Now, as measured from point O, the linear momentum vector of the mass is constant. 3 statements are given. You just have to mention whether out of these 3 statements, which is correct statement. More than one statements may be correct. B is value of linear momentum of the mass depends on relative position of point O on the axis. Relative position of the point on the axis. On the axis means the point can be here, it can be here, it can be here. You can change the relative positions. And there is a third statement which cites the value of angular momentum of the mass depends on the relative position of point O on the axis. So based on discussions so far, I would like to have your inputs. And again, I'll request, I will wait for 2 minutes. Let us receive your answers in the chat box. More than one options may be correct. I hope we are receiving the answers in the chat box. We would be happy to receive 100% responses from all the participants. Neetu ma'am or Meenakshi ma'am, could you help me in?
The C is dominating.
Okay, then I think we need not
Maximum
discuss.
answer is for C.
Okay, so I'm happy to
Yes,
receive.
sir.
I'm happy to receive maximum options as C, and it is correct. So I need not discuss it much. First two are related to
Someone
linear.
has shared B.
Okay.
So someone has shared B too.
Okay. Okay. So second point I will discuss. First point, obviously, linear momentum, mass into velocity. Velocity is along the tangent. Here the tangent will be in this direction. Here the tangent will be in this direction. So direction of velocity is changing. One thing we should note here, the linear momentum vector of the mass m is constant. No, it is not constant. Its direction is changing, but its velocity value is same. Second point, its value depends on the relative position of O. Now, if I happen to be here at O, or at O dash, or at O double dash, that is not going to change its velocity vector. This is one important difference between linear momentum and angular momentum. While linear momentum, which is mass times velocity, is independent. Now, this is an important takeaway from this discussion. It is independent of the observer who is observing, provided he is at rest. Any observer, irrespective of its location, the velocity remains the same and hence linear momentum remains same. But L vector, it depends on the location of the observer due to this R vector in it. So options A and B are not correct. And third point we have already discussed, as we change our location O, O dash, O double dash, C, etc., our R vector will keep on changing. And that might lead to change in the net angular momentum, its direction or magnitude. So I think this doesn't need much discussion, so I'll skip this. Now comes the same situation with next set of questions. Again, I will pause for this time more time, 3 minutes. Now let me specify that here we are talking about angular momentum as measured from this specific point O. As measured from point O. It is, sorry. The angular momentum of mass as measured relative to point O, we have indicated it as L naught vector. Now 5 options are given. The angular velocity of mass is parallel to angular momentum. L naught is equal to I omega. L naught is constant. L naught has constant magnitude. Direction is constant. So again, I'd request the participants to put the answer in the chat box. More than one options may be correct. Based on what we have discussed so far, it should not be a difficult task. But even then, some new points might come. So I request all the participants to please register your choices.
Sir, in first part, angular momentum about O we have to consider.
Yes, yes.
Okay.
So I don't want to be in a hurry. Take your time. Once we receive sufficient number of answers, we'll wait for 1 more minute. And once again, I request other participants to do register their responses in the chat box. Such related questions similar questions will be there in the assignment too. So this will help you identify answers in the assignments also. Okay, now I think, madam, have we received sufficient responses?
Yes, sir. Maximum.
Yes, sir.
So first is D. Maximum number is D. Then second B. Then A, and 1, 2 have also written E. Maximum is D. Then second is B. Then third is A, and 1 or 2 has written E.
So nice of you, madam. You gave a very good data. I am very, very happy. Nobody wrote C.
Yes.
Nobody wrote C. So I'm happy. To some extent, we can consider this to be a successful discussion. L naught is not constant. This we have already discussed. And why it is not constant? Because we have already discussed that this is R vector. And P vector is into the screen. So R cross P is this vector, which is L naught vector. Its direction is changing, so L naught is not constant. Most of you have written L naught has constant magnitude. Let us see. Magnitude of L naught vector will be magnitude of P times magnitude of r vector as seen from O. Let me call this distance as x times sine of angle between them. Now, what is the angle between r vector and this p vector?
90.
Is it always 90?
I think throughout the journey.
Yes, it is. It is because the situation is symmetrical. It is like a cone, you can see. So all the r vectors will be always perpendicular to the p vectors, and therefore the magnitude becomes p times r, which is mb times r vector magnitude, which is x. Now m is same, v is same, and x is same. Here also x will remain same. Here also x will remain same, and so on. So L naught vector is constant. Nothing much to discuss here. Now, some of you answered angular velocities, second one. Second and third, I am more interested.
Sir, how it would be 90 that if you can explain angle?
Okay. Sir, P vector, at least you can agree with me if I say that P vector is at this point. At this point, it is a cross. Cross means it is perpendicular to the plane. Do you agree with this? Hello, sir. Do you agree with the fact that P vector at this
Yes, sir.
point?
Yes, sir. Yes, sir.
Yes. And R vector is in the plane.
Yes, sir.
One is in the plane, one is perpendicular to the plane. So they are supposed to be perpendicular.
But like when it go in the 12 o'clock position.
Okay. When it goes here, nothing you have to do, sir. Just change your orientation. You hold your screen, turn it by 90-degree, and imagine yourself to be at that position, and then you can figure it out yourself.
Sir, I
Okay, sir.
have one question.
Yes, ma'am.
Every time we are considering that the orientation of this motion is as given in the picture. Am I right?
Yes.
We are not changing the orientation.
Okay.
No, I'm asking this as a question. I'm not suggesting anything. I just want to understand because the moment you change the orientation, then things might change, correct?
Orientation means orientation of the entire setup or
The
position
the
separate?
motion, the motion, the dotted line that you have shown, the orbit, the
Huh.
orbital that you are showing. If I change the orientation of the orbital, then x will change.
Yes.
So in that case, things might not be same. So when you are giving this conclusion, it is restrictive to this particular orientation only.
Yes.
Okay, I
You
just wanted to understand that.
Yes, you are 100% correct, madam. In that case, whether we change the orientation or whether we change the point of observation to some other point, say P, are these not the same things? Relative to
Uh,
point P, it is tilted because relative to point B, the center is
uh-huh.
something like this.
Okay, so you
So,
mean to say the observer is also changing the position?
whether either you do this case one or case two, which you are saying that the observer
Mm-hmm.
remains there, the orbit
Huh.
gets.
I was actually meaning the second situation.
In this case, in this case, the x, if it changes, the angular momentum
Huh.
will change.
Okay, understood, sir. Thank you. Thank you so much.
Now I'm interested in the second and third responses, means options who have opted for A and B. First sentence, it says the angular velocity of the mass is parallel to the angular momentum. Parallel to the angular momentum. Angular velocity and angular momentum. Now, angular momentum we have already discussed. It is like so. Angular velocity. How do you find the direction of angular velocity? Direction of angular velocity, I'm not going to definitions. As per definition, it is along this omega vector. A right hand rule we can apply. So the plane, the omega vector must be perpendicular to the plane of rotation of the object. And L naught vector we have already discussed. Here it is like so. If you choose this point, L naught vector is like so. This obviously denies the Option A, L naught vector and omega vector when observed from point O. One more thing, omega vector does not depend upon the location of the observer. Omega vector has to be along the axis, which is represented in the figure like so. Now, if L naught vector is not parallel to omega vector, so it is clear option A is not correct. Option number B, can we say L naught vector is equal to I omega vector? Can we say this relation? L naught vector and omega vector I have specified here, they are not parallel to each other. Now this is a vector relation. Left side there is a vector, right side moment of inertia will have a value mr square, which is like a number. The vector part is omega vector. If I am writing L naught vector is equal to I omega vector, should it not mean that L naught vector direction is parallel to the direction of omega vector? But just now we discussed in this figure that L naught vector and omega vector are not at all parallel as far as point O is concerned. So my question is, can we write L naught vector is equal to I omega vector?
That is with respect, if it is with respect to point C, it is correct, right?
No, we have mentioned here from point O.
Yeah, so with point O it is not correct, but if it is with respect to C, it would have been correct.
Yes, yes. So this is the key takeaway. The relation L is equal to I omega, which we often use, should not be interpreted as P is equal to MB, analog in rotational case. Whether it is point O, whether it is point C, whether it is any other point, always P is equal to MV. But always L vector is not equal to I omega. So this should not be considered as a statement. It may be equal, it may not be equal, as madam suggested. If we consider point C, then we might be writing this equation that LC vector is equal to I omega vector. But if we choose point O, LO vector is not at all equal to I omega vector, not only in this direction. We'll see its magnitude also, it will not be equal. Hence option A is wrong. Option B is also wrong. Option C is wrong because its direction is changing, but its value is same. So most of you have opted for option D. Option D is correct. And the direction of L naught remains fixed. That is also wrong. With this discussion, yes,
one
sir.
point I clarification there. Actually, the L naught is equal to I omega. Yeah, as you said, that L naught, direction of L naught, direction of omega need not be parallel. Even if if you treat as a tensor quantity, that is generally valid for O or C. So if O means automatically L naught and omega is different direction. If you keep with respect to C, it will be same direction.
Yes,
so,
sir.
So if I is a tensor, then see the equation is valid, but one case it is only just number, another case it is a tensor. So the tensor means automatically omega and L naught will be different direction, as you pointed out with respect to O.
Yes, sir. So here, sir, actually +2 level, the idea of tensor is not introduced to the students. Here we are treating I as mr square, just moment of inertia of this mass from the axis. If this distance is say capital R, then we'll write this as mr square. So we cannot talk of tensor.
I understand, sir. I perfectly agree with you. But only thing is, we cannot say that L naught is equal to I omega is not valid. That statement cannot be correct. Still valid.
Okay.
The only thing is the I there in that case I is a tensor.
Okay. So let me specify one thing in bracket here. Here we are treating I as a scalar. If we are treating I as a scalar, then we should be cautious to use the relation L is equal to I omega. That will depend upon the choice of reference which we are considering. Exactly similar situation, point of observation, if it shifts from point O to C, and same set of questions. Now I think it should not take much time. I think 1 minute should be sufficient to have the same set of questions. Only thing we have changed here is this LC. The angular momentum of the mass m relative to point C is LC vector, and all those options which were there in the previous question, same options are there. So I would like you to please put up quickly the responses in your chat boxes. Most of these things have already been discussed and has been responded from learned colleagues. So I don't think there should be problem. But take your own time. We'll wait for 2 minutes. Let's have your responses first. Again, more than one options may be correct. So you might give multiple options as your responses. We would be happy to receive more responses. More responses are awaited. Once again, I would request all the members to kindly participate in this discussion and do respond in your chat boxes.
Sir, majority responses received are all options are true, except one or two who has given the A response as a true.
Yes, it is correct. Most of you have opted for all the options. In this case, all the options are correct. We have discussed that as measured from point C, LC, its value will be m times v times radius of this circle, which is r. Its value is constant, and direction we have seen as measured from point C, r cross p will be always upward. So the LC vector will have a value mvr in upward direction. It will be constant, and it will be in the direction of omega vector. So LC vector is parallel to omega. In this case, we will be writing safely LC is equal to I omega. Let us see. MVR, V we can write as omega times R, again times R. So this becomes MR square times omega, and this MR square, we call it as I about this axis, and therefore it has a value equal to I omega. So second option is also correct. LC is constant, we have discussed just now. And if LC vector is constant, then it has a constant magnitude, it has a constant direction. So most of you have responded correctly. So this need not be discussed much. Now the situation is changed. Case 2. Consider a similar situation with a system comprising of two identical masses. Now here there is a change. Instead of one, we have two masses. And these two masses are identical. They are identical masses. Moving at same speed v. So its mass is m, velocity is v. Mass is m, velocity is v. But the direction of velocities are opposite. And these two masses always lie diametrically opposite. Diametrically opposite to each other. So they move at speed v in circular path of center C such that the two masses always lie symmetrically opposite to center C. Is this situation clear? So this mass, if it is going like so, this mass is coming like this. After some time, this mass will come here, the other mass will come here, and so on. So they are moving in circular orbits with common center in a horizontal plane. So this was the situation. Let's see the set of questions now. Now there are two choices here, not choices, two statements. You have to identify correctness of each statement. As measured from point O, again, the net linear momentum of the system is constant. Second, the net angular momentum of the system is constant as measured from O. Which of the statements are correct? Please put in the chat box. You take your time. Now instead of one, we have two masses. So take some time in analyzing. No hurries.
Sir, masses are same or different?
Masses are same, sir. Let me once again repeat the situation. Both the masses are same, m. Both the speeds are same, but they always lie diametrically opposite. Relative to each other, they are moving in opposite directions, and their axis is common, path is common, center is common. In a symmetrical situation about point C. And this is the question. Ma'am, have you received some responses, sufficient responses?
Yes, sir.
And what are they?
So they are saying that both options are true.
Okay.
One new response: A is false and but B is true.
Okay. So let us go one by one. Let us first talk of the linear momentum. In this particular snapshot, of course, it is a dynamic system. The masses are revolving. If you take a snapshot and suppose that snapshot looks like this, at this point, its momentum p1 vector will be mass m, velocity v, and its direction will be into the screen cross. And here the second one, its momentum, which I write as p2 vector, will be again mass times speed, and its direction will be it will be coming out of the screen, so I'll represent it by dot. So the net momentum p1 vector plus p2 vector will be mv cross plus mv dot. So they have same magnitude and directions are opposite, so it comes out to be 0. And this will be true at any other situation. Therefore, the net momentum p net of this system is 0 as measured from O or C or any point. Momentum has nothing to do with the choice of location of the observer. So option number A is true. Now we have received a false statement for A. So can I have the see, the idea is not about discussing whether some statement is right or wrong, but it will help us in discussing the ideas. Why do you, whosoever responded false, would you be kind enough to share what was your uh, line of reasoning?
Actually, I forgot to add both the momentums.
Okay.
That's why.
Okay.
So I just thought of कि जो है वो momentum is vector quantity and single particle के point of view से मैंने उसको.
That might happen. Okay. But here directions are opposite, so the net momentum will always be 0. The same idea we can arrive from this fact. That the net force on this system has to be 0. So it's always good to have different lines of reasoning. This was first line of reasoning, which is merely observation. Second, why I say 0? Both the masses are identical. Number one, they are moving in circles of same radius. Therefore, their force on the first particle, which I call as F1, should be towards the center. Force on the other particle should also be towards the center, which I call as F2. Now, since this F1 is the net force, I'm talking about the net force on mass M1. This F1 will have a value, how much? This will be mv square upon r, where r is the radius of this circle. And what will be F2? F2 will also be equal to mv square by r. So these two forces, centripetal forces, have same magnitude. They are the net forces on mass 1 and 2, and their directions are always opposite. So this gives us the clue that the net force on this system of two masses, on this combined mass we choose as a system, net force on them has to be zero. And if net force is zero, dp by dt has to be zero. And therefore net P has to be constant. Now let us come to the second point, the net angular momentum. We have already seen the angular momentum for one of the masses. So for one of the masses, this was our r vector. P vector was into the board. Where was L naught vector? It was like this. And likewise, L naught vector will be for this. So this is for particle 1 and this is for particle 2.
ये मेरे टेस्ट का क्वेश्चन है ये मेरे टेस्ट ये इनको रटा
Now we can see that their horizontal components they cancel.
ये मैंने इनको पागलों की तरह बोल बोल के इनको याद करवाई चीजें क्योंकि ये तो बच्चे गलत करते ही करते
Ma'am, I request the host, somebody is speaking. Could you ask her to mute? Thank you, ma'am. तो यहाँ जो है, in this case the horizontal components cancel, the vertical components add up, and this remains the same in all the situations. This situation is symmetric. The direction remains parallel to omega vector. It is in vertically upward direction, and its magnitude will also be fixed. That is the vertical component of L01 vector and the vertical component of L02 vector, and that will give us the net angular momentum, which will be constant as seen from point O. Let us proceed further and we'll see some interesting results. Now there are three statements here again. So when we had one mass, the angular momentum was not constant, but when we have two identical masses placed symmetrically about C, we observe that the angular momentum is constant in magnitude as well as direction. Now let us revisit the similar questions which we had done earlier for this case, second case. First statement, the value of linear momentum of this system depends on relative position of point O, linear momentum. Second, L naught vector. What is L naught vector? Let me make it very clear. L naught vector is the total or the net angular momentum of the combined masses as a system. It is parallel to angular velocity omega, and in this case, for the revolving system of two masses, L naught vector, the statement says, is equal to I omega vector. The angular momentum is being measured from this point O. Earlier also we have done similar questions, but this time we have two identical masses. So let us take 2 minutes to receive your responses. I request all of you to put down your responses in the chat box, please.
Sorry, sir, I could not understand the relative position of point O. What is the meaning of that word?
Relative position of point O on the axis means if I have to remain on the axis, but my point of observation is changing on the axis from O to O dash to O double dash and so on.
Okay, thank
I
you.
have to remain on the axis. A is about linear momentum, B and C are about angular momentum.
Sir, we have to specify whether all the statements are correct or not. Am I right to understand?
Yes, you have to choose the correct statements. More than one statements may be correct.
So in the B option, the omega angular velocity is the combined velocity.
Yes, sir. Actually, omega, sir, we will discuss this also. Omega, we do not define for a particle. We can define for a particle, but this is omega of the system. And that is same as the omega of the particle. It's not correct that if I write omega vector is the omega of this particle is omega, for this particle is omega, in upward direction. So net omega is not 2 omega. If needed, we'll discuss this point. For single particle also, if it is moving with speed v, omega is its angular velocity. For this combined system also, omega is the angular velocity. It is how much the system is turning in a given time, that angle by time, that is omega.
But so that would only be in case when the speed is same.
Speed is same, sir. It was given earlier. Earlier we have discussed दोनों masses same है, both the masses are same, both the speeds are same. Center same, orbit same, everything. And they are diametrically opposite to each other.
Participants are requested to mute yourself. Only unmute when you have to answer, when you have to take part in discussion. Please.
Sir, over here, I is for the whole system?
Yes, sir. For the combined system. No hurries, please take your time and respond after giving sufficient thought.
Please mute yourself. All participants are requested to mute.
Okay, ma'am, have you received some responses?
Yes, sir, we have got a response. B and C is almost the same. Almost the same. And very few, only 2 or 3. One is very interesting response, and that is all 3 are false.
Okay.
Yes.
Okay. So then that means we need to discuss slightly. So let us see one by one. The value of linear momentum. First, we have to discuss two things. First is linear momentum. So linear momentum we have already seen. It is a 0. Just in the above problem, we have discussed the net momentum of this system is 0 because always the two masses are moving in anti-parallel direction. So their momenta are in opposite directions, so they cancel. Now let's discuss about angular momentum. Before going to options, let us first calculate the angular momentum of the system. I'd request sincere attention. Let us calculate. It will be a bit mathematical. So as we have discussed earlier, the angular momentum of the first mass, which I call as L0 of 1, it is in this direction. And it has two components. One we can write towards the center and the other will be vertical. Now if this angle is theta, can somebody state the horizontal component will be how much?
Cos theta.
No, sir. This angle will be 90 minus theta, I think.
So horizontal would become cos theta, sir.
Yes, sir. Yes, sir. You are right, sir. So this will be L0 1 sin theta, and this will be L0 1 cos theta. Exactly similar thing we can do over here. There will be one component in the horizontal direction towards center, one will be vertical. So these horizontal components will cancel. So the net angular momentum as measured from point O, when we do the vector sum of L0 1 vector and L0 2 vector, so their horizontal components cancel. So the net answer will be L0 1 sin theta plus L0 2 sin theta. This is L0 2 sin theta. Clearly this is in vertical direction. So this option B is correct. L0 vector is parallel to omega vector. So this is the value and its direction is vertically upward. Now the symmetry of the situation demands that L0 1 and L0 2 have same value. So this I can directly write as twice of L0 1 sin theta. Now how do you find L0 1? Let us concentrate on this mass. L0 1 was the angular momentum of the first mass, which is the magnitude of cross product of this vector r cross its linear momentum times sine theta. 2 into this is r, this length is r, and the radius is suppose capital R. So r into p is mv, and r and p between them the angle is 90 degree. We have discussed this earlier. Times sine theta. Now in this triangle we can see what will be sine theta, that is perpendicular. That perpendicular will be the radius, this radius capital R, upon hypotenuse, which is small r. So this is small r cancels. So we get twice of mv sine 90 is 1 and r. And v of this particle, if omega is the angular velocity, then v will be omega times r. So the entire thing becomes twice of m into omega r into r. So our L0 vector has a magnitude twice of mr square times omega. Now if we have got L0, let us quickly see what is our angular momentum. Sorry, moment of inertia. Moment of inertia of the first mass is mass into distance from the axis. The distance from the axis is r, so r square. And for the second mass is again m into r square, that is twice m r square. This 2m r square is the moment of inertia, and therefore our L0 vector becomes, has a magnitude I times omega. And what is its direction? Its direction is vertically upward, which coincides with the direction of omega. So what did we find? We find that option B is correct and option C is also correct. For this revolving system, L0 vector is equal to I omega vector as measured from point O.
Sir, excuse me, but aren't we referring with point O and that R will be our small r there, not the capital R?
Which one, madam?
Because O is relatively changing, no?
No, O was relatively changing for point A, not for B and C.
Oh, okay. Fine. I missed that. Sorry.
For point B and C, we are fixing O.
Okay.
Sir,
I missed that. It wasn't so clear here. I didn't realize it. Yeah.
But I will submit one thing here. Even if you shift O along the axis, L0 will be equal to I omega. That probably, if time permits, we can discuss. Somebody
Sir,
was saying something.
yeah, I was asking, since O is the relative position, won't the linear momentum of the system depend on that? Because if the O changes, it should change, right?
No.
It won't. It will only depend on the radius of that orbit.
Okay. No. Regarding linear momentum, you are asking, ma'am?
Yeah, A option.
A option. Okay. Linear momentum of one of the masses. Let us consider this mass. Its mass is m and it has some velocity. Let it be v vector. Now suppose instead of point O over here, let us switch to some other point O dash. Now with respect to O dash, is m changing?
No.
Is v changing?
No.
If m and v are not changing, the p vector remains same.
Okay.
For the first mass. Okay. And for the second mass also, m into v vector remains same. And they are in opposite direction. So if the first vector I am writing as mv vector, the second vector will be minus mv vector.
Okay, so it means that, so we are not talking about the individual momenta here, we are talking about the system, the net linear momentum, which will always be zero because of the orientation and the configuration we have chosen.
Yes, but even if we talk about a single mass, suppose only one of the masses were there, still the momentum will not depend upon the position of the observer, because the velocity is independent of the position of observer.
So O is the observer here.
Yes, Even if the observer is O dash or O double dash, the linear momentum is not going to change neither for the system nor for the isolated mass.
And even if we are not on the axis?
Yes, if I am at some point A, the linear momentum will remain 0.
Okay. Okay. Thank you so much, sir. Thank you.
Okay. But not the angular momentum. Angular momentum, earlier we had discussed, it will change from the perspective of the observer, from
Right. Yeah.
the location of the observer.
Yeah. Angular momentum, yes. Okay. Thank you.
But
Thank you.
not in this case. But again, not in this case. See how many interesting things are coming out. In this case, I have proved that the total angular momentum is equal to 2mr square omega. Now let us dive deep. Now suppose I go from point O to point O dash. If I shift from O to O dash, does this result, just see the result. 2 is a constant, it will remain there. Mass m is not changing. This r is radius of the orbit. Radius of the orbit has nothing to do with the location of the observer O dash or O. And omega also remains the same. So again we will get the same answer. So whether we are at O, whether we are at O dash, whether we are at C, in this case of system of two masses placed identically about point C, always we will have this situation that L as measured from any point. So I am not writing C or O dash, any point on the axis, that will be equal to I times omega vector. If you remember the earlier
just one small point. Even two masses, even four masses opposite to each other, six masses opposite to each other. So all the entire circle, I think, yes, right? Is it the correct way to think? Except the final result.
Sir, I could not hear properly, but what I got it from you, probably you said that if you have 4 masses or 6 masses or 8 masses, as long as there is symmetry.
Yes,
as
exactly.
long as there is symmetry,
yes, exactly.
This result will hold true. Yes, sir, you are right.
Yes.
And just to bring that point, I first took an example of single mass where symmetry was missing. Then I placed two masses where there is symmetry. Just as pointed out by sir, instead of two masses, if I have 4 masses, like so, then 6 masses, but all those should be symmetrically placed around C. In all such cases, we will have this relation L vector is equal to I times omega vector. Instead of point masses, if we have symmetrical distribution of mass in a continuous phase, for example, if I have a ring, for a ring also, if it is spinning about the center, we can write L vector is equal to I omega vector. But if we do not have a symmetrical distribution of mass, if I have mass of 2m here and a mass m here, then about this axis, L naught vector will not be equal to the moment of inertia about that axis times omega. So nice point raised by you, sir. Thank you.
One more clarification, sir. One more small clarification. Previous to previous problem, where you were talking about the single point, single mass. The previous to previous problem. Can we go to the previous to previous problem? Single mass we were discussing, right? About O, about C.
Sir, 1 minute.
Single point. Single.
This one, sir?
So in this case, in this case, we talk about suppose instead of choosing the point C, if I choose some other point, but it is still in the circular plane, maybe not at the circumference or middle, just exactly. Somewhere, some other point we choose some point O prime, some B. So with respect to this point, can you describe how the L? So L is full I omega. Can you just elaborate how the L will change, how the L look like? Same or different? Just kind of my.
Okay, sir. Let us see the I which we are discussing here. The I of this mass, let us call it as M, is measured relative to this axis. This is the axis of rotation. So how much is our I? Our I is mass times r square, no doubt about that. And omega, no doubt, omega remains the same. If our point happens to be somewhere here, as you told O dash. Let us consider this point to be O dash. Then our L vector, which we have to find, will be R vector at this point, cross P vector. P vector in this situation is into the screen. So R cross P, as measured from this point, will have some direction, but what will be its magnitude? Its magnitude will be L as measured from O dash will be equal to magnitude of R as measured from O dash cross P. R as measured from O dash has a magnitude, suppose call it as D. Let this distance be D. So this will be D into P vector. P vector is how much? MV into sine of angle between them. Now that sine of angle between them will be something. This may not be 90 degree, and it in general will not be 90 degree. Let us assume it to be something, say theta. So this will be m times v times d sine theta. Now where that mass m is located, don't you think that theta will continuously be changing? And if theta continuously changes, will my LO dash vector not change continuously? So it will change continuously. And if it continuously changes, can I write it to be equal to mr square omega always? There might be a situation wherein it might be at momentarily have a value equal to mr square omega. But the value of d and then sine theta, will it not change? So except at point C.
I think the direction is remains same. The magnitude may change, sir, as you pointed out.
Yes.
Direction is still perpendicular.
Yes.
The magnitude is, as you pointed out correctly, keep on changing.
Yes, magnitude will change. Direction is, in this case, it will remain. Of course, it depends.
Because the R and P are in the same plane, right? Because R and P are in the same plane, automatically L has to be perpendicular to the plane, right?
Yes.
Because anyway R cross P.
Yes, sir.
So, if we choose the point C, both magnitude and direction same. We choose other than point C in the same plane, only direction same, but magnitude keep on varying. So that is the conclusion we can make.
No, sir.
There
may be some points. There may be a point in the same plane about which the direction also does not remain same. Direction because there might be some point on the orbit.
No, sir. Because my point is, even if you change any point in the plane, in the circular plane, because anyway R and P is in the same plane, right? If R and P is same plane, automatically the R cross P always perpendicular, right?
You are right, sir. But I cannot say that the direction remains constant. Why? Just consider my point. Suppose this is the orbit. I choose a point on the orbit itself. Let me call this point as P. Is this point lying on the plane or not? Yes, sir. So there will be a moment when this mass m will reach to point P. When this mass m reaches at point P, the mass is at point P itself. So what will be the angular momentum? It has to be 0. When there is no angular momentum, there is no question of direction. But the same mass, if it is at somewhere else, like so, there will be some r vector. And as you pointed, r vector and p vector are in same plane. So there we will talk that yes, angular momentum is perpendicular to the plane. At all those points, it will be perpendicular to the plane. But there is one point, if I choose a point on the orbit itself, one moment will come in every round when the angular momentum will become 0. When it will become 0, I cannot say it is pointing in upward direction. That is just what I wanted to add to your argument. Otherwise, if you leave that point, what you are saying is 100% correct, sir.
This is the excellent point, sir. Which is the point you proved that if the mass travel the same point, your reference point, automatically L is 0. That is interesting
Yes.
conclusion.
So that's why what you are telling is correct, but we cannot generalize it that if it is in the plane, it will have same direction. That was my point, sir.
In fact, like as it will come closer to P, the arm length will also reduce. So it's like if you look at it, it will become maximum diametrically opposite, and then as it is coming closer, it will assume its minimum, and then again start to increase as it goes away.
Yes. The value will change. The arm length, yes, sir. The arm length will change.
Sir, just a thought. Let's say if we take this, if we go back to the situation that we were discussing on the axis itself.
Second one.
The current the thing only that we were discussing. So let's say if we take this point O very far away.
Okay.
So in that case, like again, it'll I think the sign will as theta will tend to 0. Again, it'll.
Okay. Yes, sir. I got your point. Because if you go very, very far, this entire depends how far. If you go very, very far, much larger compared to R. Suppose your D is very, very large compared to R.
Yeah.
Then you don't see it as a circular orbit. You see it as a point.
We don't see it as a orbit only. That yes, correct.
So you don't see any change. So for that, there is no change in angular momentum, and probably will not change, but depends how far. If the size of the orbit is very, very, but strictly speaking, if you have a finite distance, there will be some L.
Yeah.
All those things which we have discussed so far will hold true. We have reached just to the end, so I would like to conclude only. Madam, can I take just 5 minutes? If the participants allow me, just 5 minutes, I'll conclude. Nitu ma'am, can I take just 5 minutes more? Meenakshi ma'am, am I audible, dear colleagues?
Yes, sir. Sure, sir.
Yes, sir. That'd be great,
Thank
sir.
you.
Thank you.
Let us now, after all this discussion, put the last choice in your chat boxes for these two statements. We have already had the discussion. The value of angular momentum of this same system of two masses depends on relative position of point O, and second one is L as measured from O, from C, or from other point P is same as I omega. Quickly submit your responses based on what we discussed so far. I request all the colleagues, dear participants, to kindly put in their final responses for today's session. O and C we have already discussed. Just I have put an extra point P. We are receiving the responses. I would be happy to receive 100% responses. Namaste Neetu ma'am, could you help me in identifying the responses? Pragya ma'am, are you there? Okay, no problem. Then can I receive the response from the participants only? Can somebody please see the chat box and tell me what responses we have got?
The maximum B.
So
Some
mostly
has opted option A also.
Okay. Okay. So just now we have discussed.
Mixed answers are there.
Okay. Thank you, ma'am. Just now we have seen, while we discussed here, the total angular momentum as measured from point O, we got this answer. 2mr square omega. Now I discussed earlier the 2, the mass m, the radius r of the orbit and the omega. Nothing is going to change. Nothing out of these depend on the relative position of O. So for such symmetrical systems, the value of angular momentum does not depend upon the position, not only on the axis, irrespective of any observer. I choose a point over here A, I choose a point over here B, I choose a point over here C, upstairs somewhere here D, any point we choose. It is very interesting. In all such cases, the angular momentum for this system will be twice of mr square omega, that is equal to I times omega. So,
Jeevan sir, sorry, I couldn't attend.
No, madam, I received the responses
because at that time I was unable to unmute
Yes.
myself.
So actually, the today's session has been conducted in the very interesting manner, starting with fundamental concept of rotational motion. Very interesting problem on the inclined plane by taking 3 bottles, and that was explained thought provoking in very good manner. And after that, very informative and interactive, all about torque, angular momentum, by taking the various cases. And moreover, participants have also participated very enthusiastically. And here today, most of the parties.
I think there are some connectivity issues with the Meenakshi. Hello, Meenakshi ma'am. No issues at all. Thank you so much, sir, for your so kind and interactive session. So I am sure that our participants will be benefited a lot with this, and hope to see you tomorrow.
Okay, thank you, ma'am.
There's one more session. Dear participant, we will share the feedback form in your WhatsApp group. So please share your feedback.
Madam, somebody has raised the hand.
Yes, Shashank Verma has raised a hand. So please unmute yourself.
Yeah, ma'am, if it's okay to ask a question to sir, if that's okay. If it's
Sure, no, you can.
yeah.
You can.
Yeah. So, sir, one thing I was thinking about, sir, I don't know this fully, exact how it relates fully, but I read somewhere that conservation of angular momentum is because it comes from symmetry, essentially, both linear momentum and angular momentum from different symmetries. So, like, is there a deeper insight that you were trying to explain here? Like, is there a deeper meaning behind this, that in symmetrical situations only the angular momentum is being conserved, whereas in other situations it's not being conserved, and it's depending on different observers? Yeah, that's something I wanted to ask, sir.
So the very key word, the key word, what you told is a symmetry. And that's what I tried to bring in. I first took a single mass, then I took 2 masses, and as was pointed out by distinguished colleague, that if we have symmetrical masses, then the angular momentum as measured from any point will remain same. Now, that was the key idea which I wanted to bring in. It's not about the conservation. Conservation will depend whether or not there is net torque. But then if we have a system which is symmetrical about its axis, and it is spinning about that axis. Let me give a very simple example, and this will be the gist of today's discussion. You choose a planet, let it be our Earth. Earth is spinning about its own axis, and Earth is revolving around the Sun. Now, if we consider its rotation about its own axis, and we assume that the Earth is a sphere, then this is a symmetrical situation. So in this case, its angular momentum will remain same whether I observe it, whether a person in the sun observes it, whether a person inside the earth observes it. Irrespective of the location of the observer, it has a constant angular momentum that we call as a spin angular momentum. But if we talk of the revolution of the planet, the earth around the sun, it is not a symmetrical situation. In that case, the angular momentum of the earth, as seen by different observers, will have different directions. They can have different magnitudes at all. That was the gist of today's discussion. And from my side, I thank all the participants. It was a very nice discussion. बहुत मजा आया, आनंद आया. And I once again thank the IPT team, Nitu ma'am, Meenakshi ma'am, for giving me this opportunity. Let's see if I can do justice tomorrow also. I'm sorry I could not finish all the things which I intended to say, but whatever I discussed, I hope it sunk in through your minds. Thank you, everyone. Sabhi ko namaste.
Thank you
so
sir.
much, sir.
Thank you,
I think,
sir.
sir. Yeah,
Good
sorry.
evening. Good night to everyone. Hope to meet you
Yeah, thank you, everyone.
tomorrow. Okay, bye.
Thank you, sir. Thank you, ma'am. Ji.